All right, so today we are doing trigonometric substitutions. And for the warm-up, if you know that x is a sine theta, is that enough information for you to figure out what cosine theta is? Well, it is if you draw a triangle. So think of sine theta. We know that sine theta is opposite over adjacent. Sorry, I said opposite over adjacent. I'm thinking tan. Sine theta is opposite over hypotenuse. And so we're given that x is a sine theta. Solving for sine theta, we have x over a. So on our triangle, on the opposite side from our theta, we can label that as x. And on the hypotenuse, we can put a. And then solving, knowing that a squared plus b squared is equal to c squared, because this is a right triangle here, we can solve for the other leg, the horizontal leg. It is the square root of a squared minus x squared. And so now our question was, can we find cosine theta? Cosine theta, that's adjacent over hypotenuse. And so our adjacent, looking at our triangle, that's going to be the square root of a squared minus x squared. And that is over the hypotenuse, which is a. And a is just standing in for some constant, some number. Questions on that one? Okay, do you feel like you could do this if you had to? Okay, great, because this is the premise of today's lecture. So let's take a look, kind of big picture here. All three of these triangles are filled in, and I'll go back, I'll refer to them in a few minutes. And then you will also have this in your completed lecture notes that you can refer back to it as well. Yes. I'm sorry, you're going to have to shout. Like a squared plus b squared equals. Well, I do want you to do it this way because this is what's going to help you with the integration that we're doing today. Great. All right, so let's, for our first example, we want to integrate dx over x squared times the square root of 4 squared minus x squared. Okay, so this looks a lot like the homework problem that you did that was due yesterday, except for in that homework problem, there wasn't an extra x squared. And so you could integrate that using techniques that we already knew. Here, if we try to let u equal 4 squared minus x squared, taking a similar approach to what we did on that homework problem, we get into trouble because we don't have that 2x or negative 2x dx in the numerator. So there's no way to make this into a u sub. But, oh, there's a lot on that side. That square root, anytime you see the square root of 4 squared minus x squared or x squared minus 4 squared or something along those lines, that's your clue that you should think trig sub, assuming you can't do u sub, of course, and that is not one of the other techniques, partial fractions or integration by parts. So usually that square root is going to be a key to think, oh, maybe I should do trig sub. And the square root of 4 squared minus x squared, it's similar to that first slide where we had the square root of a squared minus x squared equal to a cosine theta. And so in this case, our a would be 4. And label that on our hypotenuse. And then going over to sine theta equal to x over a, if we solved for x and plugging in 4 for a, that gives us that x is 4 sine theta. And using the same principle, the same way we did on the opening slide to solve for that square root part, we're wanting to seeing how far I filled in here. Okay, so let me back up and write what we had on the previous slides so we don't lose that. When we're looking for our substitution, we're always wanting to keep it as simple as possible, and we need x equal to something. So we're always going to relate x and the number. And so that is why in this case, when we're looking for that relationship between a and x, it's sine theta. And we'll talk more about that as we go through more examples. But for now, let's just roll with it. And x is 4 sine theta. And just like when we do any type of u substitution, you need your dx. So the derivative of 4 sine theta is 4 cosine theta d theta. And our goal, we have this square root of 4 squared minus x squared in our original integral. So we still need to figure out what can we substitute in for what can we substitute in for this square root part? Now, we know that x is 4 sine theta, so we could sub that in. We could square it. We can use the Pythagorean identity, cosine squared plus sine squared is equal to 1 in order to simplify, but that's so much work. Instead, go back to your triangle, and we're looking, we want, in order to figure out what to substitute in for the 4 squared minus x squared, we're looking for a relationship between the square root part and the number, because we want to keep it as simple as possible. If we somehow brought this x into our equation, then it makes it a lot more complicated, and we don't have that extra x up here. So we're looking for a relationship between 4 and the square root of 4 squared minus x squared, and that is cosine theta. So cosine theta is adjacent over hypotenuse. Adjacent is the square root part, the hypotenuse is 4. And if we solve that for the square root part, we get the square root of 4 squared minus x squared is 4 cosine theta. So going back to our original integral at the top of the page here, in place of the square root in the denominator, it is being kind of glitchy today. In place of the square root in the denominator, now we can substitute in 4 cosine theta. In place of the dx in the numerator, we can substitute in 4 cosine theta d theta. And I'm going to highlight these so you can see that even though we're putting a cosine in the numerator and in the denominator, they're related, they're different cosines. The blue one, I'll just stick with the yellow. Okay, so the yellow, that's where we're getting the 4 cosine theta in the denominator, and then the 4 cosine theta d theta in the numerator, that's coming from the dx. And the last piece of our integral, we have this x squared, but we know that x is 4 sine theta. So in its place, we can substitute in our x equal to 4 sine theta. So substituting all of that into our integral, that gives us In the numerator, we have 4 cosine theta d theta. In the denominator, in place of x squared, we have 4 sine theta, quantity squared. And in place of the square root part, we have 4 cosine theta. And now we can simplify this before we integrate. This is equal to the 4's both cancel out with the cosine theta. So 4 cosine theta in the numerator and the denominator cancel out. And we have that 4 squared in the denominator. So I'm going to pull that in front of the integral there. So that 4 squared, well, that's the same color I already used. That 4 squared is coming from the denominator there. And then we have 1 over sine squared theta d theta. So I'll go ahead, I'll put the d theta in the numerator here. Sine squared theta. Okay, so we want to keep simplifying. This is equal to, we can keep the 1 over 4 squared out front. 1 over sine squared theta, that's secant, that is cosecant squared theta. So we can simplify that as cosecant squared theta d theta. And you do need to have these basic trig integrals memorized, but it's not as bad as it seems because we know the related trig function, secant squared. We know the integral of secant squared theta d theta is tan theta plus c. And so that means if we want to integrate cosecant squared theta, then that integral, I'm going to need a little more room, is going to be the negative co of what we had in the line above. So negative cotan theta plus c. Applying that to our integral, we now have a negative 1 over 4 squared. And then the integral of cosecant squared theta, I put the negative out front already, and then that is equal times cotan theta. Parentheses there. Plus c. Now, it might be tempting at this point. In order to get this back in terms of x, it might be tempting to solve for theta and just plunk it in there. So I can put this in green because you should not do this. This is what bad notation here. You don't want to write this as negative 1 over 4 squared, cotan. And let's see, if we solve for theta, then we would have theta is arc sine of x over 4. And this is bad notation. You would not get full credit for this. You never ever want the trig of some arc trig. There's always a better way. And in order to find that better way, go back to the original triangle that we've already drawn. So if we go back to our original triangle, we know that cotan theta is adjacent over opposite. And so looking at our original triangle, our adjacent over opposite, that's the square root of a squared minus x squared over x. And so we can substitute that in for the cotan theta. Leave the -1 over 4 squared out front. And that is times the square root of 4 squared minus x squared over x plus c. Okay, so ignoring the obvious question of how in the world did you know to use that substitution, are there any other questions, like just maybe on the integration part? Yes. How am I able to hear? Okay. Okay, so let's address that obvious question. How do we figure out what substitution to use? And can we generalize this approach? So let's, on the next slide, I kind of wrote out step-by-step instructions for you. So that makes it a little bit easier to follow along when you're trying this on your own. So first off, rule out U sub. Make sure you can't use U substitution. Make sure that it's not partial fractions, integration by parts, any of that. But once you know that it is a trig sub, even though we don't have the square root in here, it's still that sort of x squared plus a squared form, then that makes you start thinking, oh, this is trig sub. Okay. So we want to start by drawing a triangle which has the sum and the difference involved. And so by sum or difference here, I'm referring to, we want our triangle to involve x 3 squared and this x, the square root of x squared plus 9. So that's how we're, the variables that we're looking to relate. And in order to figure out how, which pieces go where on the triangle, let's go back to the opening slide and take another look at it quick. And my hint here, when you're setting up your triangles, is that hypotenuses love positives. And I even put this slide on Canvas under additional resources for you, under week 2. And what that means, hypotenuses love positives, is that in each of these square root pieces, whatever is positive, that's the part that goes on the hypotenuse. So in the first example, a squared minus x squared, a is the positive part, it goes on the hypotenuse. When we have something, an integral that is involving a square root of x squared minus b squared, then the positive part of that is the x squared. So the x is what goes on the hypotenuse. And then if we have all positives, so here the first term is positive, we have a positive for the constant, that whole thing goes on the hypotenuse. The other trick or little hint that I'm going to tell you is that on the vertical, there's always an x on the vertical. So look. And there we have our x on the vertical leg. The only time we don't have x on the vertical leg is when it's on the hypotenuse. And in that case, we still put the variable x on the vertical leg. So that's just a little hint to help you set up those triangles. And of course, that means your theta has to be in that bottom left corner there. So let's go back to our example. And we have all positives here, the square root of x squared plus 9 squared, 9, 3 squared. And so let's put that on our hypotenuse. And I'm going to rewrite 9 as 3 squared, just to keep it track of it a little bit better. And now you can either use kind of our shortcut here that, oh, hey, we know that we're going to put x on the vertical and a down here. Yeah, I'm going to do that. So now you have your triangle drawn. The next step is we need to find our substitution. And so we need some x to sub in. And you always want to look for that relationship of x over the constant, because this is the simplest relationship you're going to get. If you start looking for a relationship between x and you bring the square root in here, it's much more complicated and it won't work. So just think you always want x to be in the numerator so we can easily solve for it, and then over the constant. And if you've set your triangle up correctly, you will always get either sine theta, tan theta, or secant theta. It will always be one of these three. If you get a co, then stop, redo your triangle. So you should never get a cosine, cotan, or cosecant. Okay, so in our case, I kind of just went with the shortcut instead of the option of where do x and 3 go. I'm wondering if we should even go down that path there. So in option A, we already did that one. So if we follow along with that, I'm just kind of playing like, okay, so what if we didn't set it up that way? What if we set it up incorrectly? Then what would happen? So if we had set it up incorrectly here, in option B, when we're looking for that relationship of x over 3, well, now that's going to give us x over 3 is adjacent over opposite. And that would give us that cotan that I said we don't want to ever use. Theta. And the reason we don't want to ever use cotan theta or cosecant or cosine is because when you take its derivative, you get a negative. And we don't want to deal with the negatives. Also, that means that every problem that we do in here would have 2 correct approaches. And so that's really hard for us to kind of follow along 2 different rubrics there. So to keep it consistent, make sure that whatever your trig sub is, it's either sine, tan, or secant. You will not get full credit if you have a trig sub that involves one of the cotans as your, or cos as your x variable. So this is not a good option for us. And instead, in our option A, set that to a 3. When we're solving for that relationship of x over 3, now that's going to be our opposite over adjacent. Which is tan theta. Squeezing it in there. So we want to let x equal 3 tan theta. Maybe I'll come over here and do our setup. Taking the derivative of both sides, we have dx is equal to 3 secant squared theta, d theta, And then instead of just subbing in x equal to 3 tan theta in the denominator and squaring it and simplifying it, that's way more work than what you need to do. Let's instead look at the triangle to find what we should substitute in for that. So we want the trig relationship that gives us the square root of x squared plus 3 squared over 3. Because we want to relate the square root part and the constant. So we're thinking, what trig relationship will give us? Will give us that term. So we have, let's see, on the square root is on the hypotenuse. And the 3 is on the adjacent. And so what trig relationship gives us back hypotenuse over adjacent? Secant theta. And so that means if we solve for that square root, and we can multiply both sides through by 3, the square root of x squared plus 3 squared, that is equal to 3 secant theta. And you could at this point sub it in, but we don't have a square root of x squared plus 3 squared. We just have an x squared plus 3 squared in the denominator. So let's go ahead and just square both sides of this equation. And so that means x squared plus 3 squared is equal to 3 squared secant squared theta. And now we have all the pieces we need to substitute in for our integral. So in place of the x squared plus 9 in the denominator, we can substitute in the 3 squared secant squared theta. And in place of the dx in the numerator, we can substitute in 3 secant squared d theta. We never even used our x substitution because it's not involved in this integral. So let's sub those in. We have the integral. In the numerator, we have 3 secant squared theta d theta. And in the denominator, we have 3 squared secant squared theta, and that quantity is squared. So I have a 3 in the numerator. I have a 3 squared squared in the denominator, which is 3 to the 4th. So we can pull that out, 3 over 3 to the 4th, which is 1 over 3 cubed. And sure, you can write 1 over 27, but as you do more and more of these, and you don't have to, you'll find that maybe sometimes it's just easier to not even deal with that algebra, just leave it like this. So we have a secant squared theta in the numerator. We have a secant to the 4th theta in the denominator. And so that gives us just a 1 d theta in the numerator. And in the denominator, we have a secant squared theta. We can keep simplifying here before we integrate. This is equal to 1 over 3 cubed times the integral. 1 over secant squared theta, that's cosine squared theta. We have cosine squared theta, d theta. And anyone know how to integrate that? Half angle identity, absolutely. So we know, we'll kind of put a little note over here to jog our memory, that the half angle from Monday's lecture identity tells us that cosine squared theta is equal to 1/2 times the quantity 1 plus cosine 2 theta. So subbing that into our integral, we have 1/3 cubed times the integral of 1/2 times 1 plus cosine 2 theta d theta. And we are finally ready to integrate this. So this is equal to, I had better give myself some more room here. Kind of like going down in the column because I think it's easier to follow rather than doing my workout horizontally, but I'm quite pushed for room here, so we'll just kind of keep going with this. We have a 1/3 cubed. We can pull that 1/2 out front. When we integrate 1 with respect to theta, we get theta plus the integral of cosine 2 theta, which is 1/2 sine of 2 theta. Close my big set of parentheses, plus c. But we still have to get this back in terms of our original variable. So take a second, look at our triangle, and I'll give you a hint before you try it. Another trig identity that you want to make sure that you have memorized, sine of 2 theta, since you will use this one often, is equal to 2 sine theta cosine theta. So I'll give you like 30 seconds, and using that identity, can you get our answer back in terms of the original variable x and also the triangle? Okay, so hopefully you've had a chance at least to get started on this. This is going to be equal to, we'll just leave that 1/3 cubed out front. We'll leave that 1/2 out front. And in place of theta, so here it's okay to have an arc something because we're actually solving for theta. So we don't have like trig of arc trig, we just have an arc tan all by itself. So arc tan of x/3. If we went back to our original substitution up here, and we solved for theta, that's where we get the arctan. Plus, we have 1/2. And now when we substitute in place of sine 2 theta, the 2 sine theta cosine theta, I'll put the 2 out front. Sine theta, going back to our original triangle, sine theta is going to be, sorry, my page looks very different, so I can't even see the triangle where I'm looking. Sine theta is going to be x over the square root of x squared plus 9. And then, so that's the sine theta, just to make it a little easier here to follow. Sine theta part, and then in place of the cosine theta, we will have adjacent over hypotenuse, which is 3 over the square root of x squared plus 9. Close our brackets, and that is plus c. Okay. Questions on that one? Yes. Excellent question. Do we need to keep simplifying here? No, this is totally fine because I can clearly see where each of the pieces is coming into. So even though, I mean, it's really easy to simplify that denominator, you don't have to. And in fact, if you did and you made an algebra mistake or a copy error, then you could lose points. So I would encourage you not to, just leave it just like this. Yes. Oh, yes, I do. Thank you. So we need one more set of parentheses. In fact, that's a lot of parentheses. Maybe we'll just change that to a bracket. Because bracket there, because that 1 over 3 cubed times 1/2, that is multiplied through that whole thing. Thank you for pointing that out. Yes. When is the square root on the hypotenuse of the triangle, he asked. And that's only when you're going to have like x squared plus a squared or a squared plus x squared, because the positive part of the square root, that's what goes on the hypotenuse. So in this case, of this example, the whole thing was positive, so that went on the hypotenuse. In the previous example, where we had the square root of 4 squared minus x squared, the 4 is the positive part, and so that's what went on the hypotenuse. Yes. I think you asked how I got theta. Sorry, it's hard to hear. Yes, so go back to, whenever you integrate and you have theta just all by itself, go back to your original substitution. So what color have I not used? So if x is 3 tan theta, then solving for tan theta, we have x over 3. And so then arc tan is, theta is arc tan x over 3. And that reminds me, make sure that if you are taking the inverse of a function, that you write it as arc tan, arc sine, arc cosine, not as something to the -1, because that is really bad notation. And all of us mathematicians are really mad at whoever did that, because came up with it originally. Because when you have something raised to the -1, that is 1 over something. And so it just gets so confusing if you're using that notation to mean an arc sine or arc cosine type of thing. Okay, another question. So we've seen 2 of the 3 cases. We've seen in the first example where we had a number on the hypotenuse. On this example, we have the square root of x squared plus a squared, the whole thing on the hypotenuse. And in this next one, let's take a look at what we should put on the hypotenuse. Here we have x squared. This is the positive part of our square root thing. And so when we draw our triangle, we know that we want to put x on the hypotenuse. So now, in the other 2 examples, we always put x on the vertical, but this trumps it. This takes precedent because you have to set up your hypotenuse first. So that means on our vertical leg, we still want an x involved. So that will become the square root of x squared minus, I'll write that as 2 squared. And on the horizontal leg, that leaves us with a 2. So that is our triangle setup here. And now to figure out what substitution we want to use, we are always looking what trig identity will give us x over the constant. So what trig identity gives us x over 2? And x, that is our hypotenuse, over the adjacent. Oh, we should label our theta. That's really important too. Don't forget to label your theta. And so now that we have a theta in our triangle, we can see that this relationship that we're looking for is going to be secant theta. Solving for x, that gives us x is 2 secant theta. And the most common mistake I see on these is forgetting to substitute in for the dx. So make sure that you do find your dx. That is going to be equal to 2 secant theta tan theta. Usually you figure that out, that you forgot the dx part, when you are trying to integrate and you realize it's something you've never seen before. So when you get down to that scenario, just do a quick check, make sure you substituted in for your dx. And now we need to figure out what to sub in for the square root of x squared minus 2 squared. So for that substitution, we're looking for what trig relationship lets us relate the square root part and the 2. And so this is equal to the square root part, that is the opposite leg. The 2 is the adjacent leg. And so opposite over adjacent, that is tan theta. You can multiply by 2 each side. So we have x squared minus 2 squared. That square root is equal to 2 tan theta. And since we don't have a square root in our problem, you can square both sides. Now, before I let you go, I want to point out one more thing. You'll go through and you solve this, and you should, and you'll end up getting for your answer natural log of the absolute value of square root of 3, technically like minus 0. But unless the instructions specifically say use trig sub, don't use the easier method. How else could we have integrated this? Yes, use sub. How else could we have integrated it? Partial fractions. Either approach is probably going to be easier than trig sub. Okay, so tomorrow in workshop, you'll get to practice this, and you will also review completing the square. So you'll have some completing the squares on your written homework and web work. So I'll make sure the TAs go over that with you tomorrow. And a reminder, if you need scrap paper for homework, come see me.